Hi guys, so welcome to the first video on combinational logic. Here we'll try to lay the conceptual groundwork, conceptual framework for understanding combinational logic circuits. And as a bonus too, we'll solve questions at the end of these so that we leave this video understanding and being more confident in combinational logic than we were before. As we go on, we'll solve more complex problems and word problems even, so that we can get more familiar with designing and solving questions on combinational logic circuits. So what is combinational logic? Primarily, digital logic circuits, so let's call that DLC, are divided into two, okay? On one hand, you have sequential circuits, and on the other hand, you have combinational. So over the course of this series, we're going to start with combinational as most do, then we cover sequential once we're able to establish what combinational means. So combinational logic circuits means that whatever you're doing has no memory. So it's very important to know that there's no memory in combinational logic. What does this mean? It means that whatever the state is in, so let's use this to represent different states. So state 1, state 2, state 3, state 4. And let's say time goes on this way. So let's say over time, okay? States 1, 2, 3, and 4. 1, 2, 3, 4, and 5. The state of 3 is independent and doesn't depend on the state of 2 and does not affect the state of 4. So that's what combinational logic is. When you get to sequential circuits, you see that devices here under this category have what you call a memory. They can latch onto memory, they can latch onto current states, and whatever it is now definitely has a role to play in the states to come. But combinational logic is independent, meaning that whatever state you're in is not affected by what was before it, and is not going to affect the state coming up next. So combinational logic is a simple groundwork for beginning in digital electronics, and there are multiple circuits under these. You can have adders, multiplexers. So adders are, even you can actually perform addition and subtraction with combinational circuits. So digital addition, digital subtraction come under here. You have adders, multiplexers, decoders, encoders, comparators too, and parity generators. So these are all different types of circuits that we definitely get into as we proceed in the series. But this is just so we can know what these are. Adders and also subtractors can come under here too. Adders and subtractors compare binary states and perform regular addition. Decoders detect the presence of a state. Encoders perform the opposite. And comparators make as the name implies, a comparison between two binary states. So combinational logic is a very simple groundwork for getting started. Then we get over to the next thing that we're going to need, the next tool we'll need, and that's called truth tables. We actually sort of did a handful of this in kernel maths. Well, let's lay a groundwork. A truth table is a mathematical grid used in logic circuits to determine the outcome of a logic expression. So we have a handful of things. It's a mathematical grid, okay, which means that the rules of math applied to truth tables is not independent of its own, and more importantly, to determine the outcome of logic expressions. So what do I mean? Let's say we have the binary expression y is equal to a not b not c, or a into b not c or not bc. This is a binary expression. And hands off the bat, straight up looking at this, it's going to be rather difficult to tell me the outcome of this for each and every possible binary state, right? So truth tables help us. So you could draw a column for A, for B, for C, and then you have one for your outputs. Okay. So how we would solve this ideally is that we may have this column for A, this column for B, this column for C, since these are the terms in our domain. And then let's say this is for not A, and this would be our output. Y is equal to A not B C, etc. So this is the structure of truth tables. They're not really complex. They are tools that help us to determine, for combinational circuits, for sequential circuits, hey, what is the outcome? What is the outcome of this? What is the resulting output of this binary expression? So that's what truth tables are, and we're going to be using those in this series. So now we head over to basic logic gates. There are 3 basic logic gates, okay? And we'll start with those, and we'll introduce others as things get more complex. But once you start with this, you're definitely covered for the beginning, for the introductory beginning part of your digital electronics journey. So the first gate we'll start with is the AND gate. Okay. So what does this mean? This is very strict. We'll call this AND. Okay. And the symbol for AND is a dot. So if we want to say A and B, we can do A and B, or we could do AB. So it's assumed that multiplying AB together sort of means that they are ANDed. So it's convention. It's how it's done, and it's sort of implied. You usually won't see this explicitly laid out. Okay. So let's see. Drawing the logic circuit of this, you would have something that looks like the AND gate looks like this. Okay. Then yay. And then you have your output coming out this way. So if this is A, if this is input A and this is input B, and then your output would definitely be A and B, not AB. So you have to take note of this. This is the logic symbol, the symbol for the AND gate. All right. And what this AND does is that it tells us that, okay, so let's say we have A, B, and A and B. Okay. We had A, B, and A and B. Drawing each input case 0, 0, 0, 1, 1, 0, and 1, 1. So it's important to know that the reason we have four rows here, okay, 1, 2, 3, 4, is that we're going to do 2 to the raised power 2, which is 4. So if you have 2 inputs, the number of rows on your truth table is going to be 2 to the n. So given n inputs, okay, you're going to have 2 to the n output rows. So it sort of makes sense when you consider the nature of binary logic. Binary logic means there are 2. Logic circuits handle 2 states. So if I have A, if I'm doing a truth table for just A, that means n is equal to 1. And how many output rows will I have? 2 to the n, which is 2 to the 1, which is 2. Why? Because A can be 0 or 1. Does that make sense? So that's sort of why we use this to get an idea of how many rows we are going to have ahead of time to set us up. So the AND gates is a very simple expression. So it means I am only going to be high when both A and B, when both of my inputs are on. So this and this, these are both low. I'm going to have a 0. Only B is high here. This is going to be low. Only A is high here. This is going to be low. And both of these are high. So I'm going to have a 1. So this is the only case where an AND gate is going to be high, when all of its inputs are high. So granted, you may have you can even have, like, let's say 4 input AND gates, okay? Let's say C, D, E, and F going into a really huge AND gate. All right, and the logic is still going to be precisely the same. Okay, C, D, E, and F, and output X. So except all of these are high, 1, 1, 1, and 1, X is going to be 1. Only in this case. If this was a 0, if only this was a 0, X is going to be 0. If this and this were a 0, X is going to stay 0. If everything was low, X is still going to be low. And it's only going to come high when every single case is high. So that's the first basic gate, the AND gate. All right, we've seen a lot of this as we go on. The second one is simpler, sort of, but it's more permissible. Okay, it's not as strict as the AND gate, and we call this the OR gate. What's the symbol for this? You symbolize this with a plus sign. Okay, so it's sort of addition, A or B. So if I wanted to show the OR expression between 2 variables, I'll simply do A or B, okay, or X or Y, and so on and so forth. So how do I draw this? What's the symbol for this? So this is going to look something like, it's very important when drawing this that you curve your inputs. So it becomes you curve the beginning part, the left side of it. So it becomes clear from the get-go what it looks like, okay? All AND has a straight line at this, or is curved. So let's say we've got A, we've got B here. Our output is going to be A or B. Okay, as usual, this is our symbol. Okay, so now let's think. How many rows are we going to have if we wanted to draw the truth table for this? We've got two inputs, A and B, which means our n is 2. So to find the number of rows we're going to do 2 raised power n, which is 2 to the 2, which is 4. Meaning that I'm going to have 4 rows in my truth table for this expression. Okay, so let's get to work. Row for A, for B, horizontal border, and write this nicely so A, B, and A or B. Okay, 0, 0, 0, 1, 1, 0, 1, 1. So the OR gate means that I'm going to be high if any one of my inputs are high. Okay, so for the first case, both of these are low. This is going to be low. 0, 0, A is on 0, B is 1. I'm going to be high because because one of these is high. Because B is high, this is going to be high. In this case, because A is high, this is going to be high. And for the case 1, 1, even though both of them are high, given that at least one of them is high, the output is going to be high. So that's the trick with the logic OR gate. You could even have multiple of this, okay? So the thing with logic gates is that it's not really limited to, it's not limited at all to 2 inputs, okay? The same principles hold as you scale it up. So let's say we had a 4 inputs OR gate, okay? Something like this, okay? With an output this way. And we had W, X, Y, and Z, okay? If these were all 0, my output is going to be 0. Okay, let's say outputs are 5. This is going to be, this may be confusing. Output, I need a letter W, output K. Okay, so if all my inputs, let's say this is an OR gate, okay, note the symbol with the curved left side. All right, so if all of these were low, my output is going to be low. If, however, just one of these became high, then my output is also going to become high. All right, the same thing holds. If Y becomes high, this is going to stay high. If all of them become high, then my output will stay high since I have at least one input that is high. So that's the trick with working with the OR gates, okay? You're able to get a high output if any single one of your inputs comes on. So that's the trick. You've got the AND gate, you've got the OR gate. And the last thing we're going to look at is the sort of the simplest guy in the group. The not let's say not so complex, but the simplest guy in the group, and it's called the NOT gate. So what is the NOT gate? NOT gate has a couple of symbols for representing it. So let's say we had C. All right. So let's say we've got a binary variable C, and I wanted to express not C. I could express it with a bar, or I could express it with an apostrophe. So both of these are valid ways of expressing not C. It's important to note that the NOT gate takes only one input and gives out only one output. Okay? So let's draw the logic symbol for this. Take only one input. The symbol for my NOT gate is a triangle with a little cute dot at the end. Then my output. Okay? So if I have A coming in as my input, not A is going to come out. It's as simple and as cute as that. If I have not A coming into my input, A is going to come out since A not A is equal to A. Okay, so this is a binary principle. So the same thing goes. If I have anything coming into A, if I have any binary variable coming into A, C, not C is going to come out. If I have B, not B is going to come out. So that's how the NOT gate works. So it's important to know that this is the symbol. You put the triangle and you put the little bubble in front of it to symbolize the negation. So let's draw the truth table for this. How many inputs do I have for this? How many wires, how many lines of logic do I have going into my NOT gate? Going into it. So you can see there's only one here. For the AND gate, we had 2. For the OR gate, we had 2. But for the NOT gate, is only 1. Okay? So that means my number of input rows is 1. A. N is equal to 1. So the number of rows is going to be 2 to the N, 2 to the 1, which is 2. What does this mean? This means that I'm only and very simply going to have on my truth table for the NOT gates A and not A. So if A is 0, not A is 1. And if A is 1, not A becomes 0. It's really as simple and as elegant as that. So these are the three fundamental logic gates when handling combinational logic circuits. So we're going to get over to solving questions so we can get ourselves much more familiar with what is going on here. Question 1. Design the truth table where the output is 1 only when both inputs are equal. Alright, so let's think. How do we go about solving logic gate circuits? We're given a word problem. We're meant to design the truth table, meaning that we need to draw a truth table. Okay? So we have our outputs. So output is 1 only in the case where both inputs are equal. So when can my inputs be equal? The first thing you're usually going to have to do is to draw your truth table, but only leave your input rows, because that helps. That goes a long way. Okay, so let's say this is our output line. A, B. All right, so let me add to this. Let's call this A. Let's call this B. So 0, 0, 1, 1, 0, 1, 0, 1. So this is my outputs. Y. Outputs. Design a truth table where the output is 1 only when both inputs are equal. So looking at this case, we have 2 inputs. So that means n is equal to 2. And my output rows is going to be 2 to the n, 2 to the 2, which is 4. 1, 2, 3, 4. 4 rows here. QT. So when both inputs are equal. So looking at this table, when are the inputs equal? Are they equal here? No. Are they equal in this case? No. Are they equal when both of them are 0? Yes. A is 0, B is also 0. Meaning my output is going to be 1 given the question. Okay, so you have to work very closely with the question you're giving. Here, they are not equal. Low. Here, they are not equal. No. Here, 1 and B is 1. Are they equal? Yes. So see, it's very simple to draw a truth table. We've drawn the truth table for this expression where both inputs are equal. So we may go a step further, as most questions would, and ask us to draw the combinational logic circuit. So though this might look complex at first, let's see how we'll do this to demystify combinational logic circuits. So our Y output. To write the output, you need to add the terms where your input is high. Because there's no point adding where your input doesn't matter. You're only going to show where your input is high. So for the first, our input is high in 2 cases. So when A and B are 0 and when A and B are 1. So writing this in binary, A being 0 is not A. Okay? B being 0 is not B. So AB, not B. Or, in this case, AB. So this is the Boolean expression for this question. How did we come about this? You get to look at it very carefully. You only care about the rows where your output is high, which are 1 and 2. And then you go about writing the cases. Given A is 1, then not A is 0. Same thing goes. If B is 1, not B is also 0. So we get to doing that. A not, this is 0, this is 0, so that's not A not B. This is high, so that's A and B. So how will we draw this? The process of doing this is really cool. It's actually really cool. So we'll call this input A, and let's call this input B. All right. We see that these guys are going to be inverted. So we're going to end up with not A and not B. So we'll draw our inverter in inputs. Remember our symbol for not, for the not gate. All right. So meaning that not A comes out of this gate, not B comes out of this gate. All right. And then we'll join these guys together with an AND gate. So that the output of this becomes not A, not B. So you see, that's how it works. You pick an expression and say, ooh, how do I create this? I have not A, so I definitely have to make A knotted. So if this is A, whatever that comes out of here is going to be not A. since this is B, whatever that comes out of this is going to be not B. And this is our AND gate. So if not A and not B are entering, then what comes out is not A, not B, which is the first part of my Boolean expression. We carry on with this, and we need to make the second half A and B. What is this? AB is the AND gate. Remember we said that it's A or B, but it will usually be represented as straight up AB. Okay? So we'll need to do AND AB again without the negation. So how this is done is pretty cool actually. You draw lines from A. Okay? So you can bring this here. You draw lines from B. You can bring this here. Alright. So pretty close. You draw lines from B. And bring it over. So what happens now is that we've simply just brought these guys out again. So instead of, we could actually just do write A here again and B here again, but that means your inputs will be appearing in multiple places, and that's usually frowned upon. If you have your inputs coming in one place and then you just draw the line out to show that, hey, this guy is coming, I'm bringing A here to also start from here. I'm bringing B from here to also start from here. So to make your work sort of easier, you can do what I'm doing and highlight the junctions where it's coming from. Because since this touches A, since this line touches B, something may occur where you're not sure where it's coming from. But given these highlighted junctions, then you're quite certain that it's coming from A. So A and B, we've got A and B. What do we have to do? We AND them together. So we take these guys out and we have to perform the AND operation. Okay, so we remember the AND gates, same one we have here. I would do it this way. So A and B come in here, and out come AB. We're almost done. The last thing we need to do is OR them. Okay? So what's the symbol? This is the OR gates, okay? And the symbol for the OR is really this funny looking thing. So we have to do that, and that's all we have left to simplify this expression, okay? So we sort of bring these guys together so our gates doesn't have to stretch over such a long distance. Okay? And then we draw our OR gates that looks funny like this and bring out that output. So remember, this is not A, not B, and this is AB. So out of the OR gates, remember, you're going to treat these as two things being added. You're going to have not A, not B, or AB, which is the same as your output Y. So you can see it's really nice creating combinational logic circuits, although it may seem complex at first. So we're going to do one more to get ourselves really familiar with it. Draw the combinational logic circuits for the following Boolean expression. Okay? What do we have to do here? We have Y is equal to not AB and A not B. Remember, we're going to start from the truth table, since the truth table makes drawing things easier for us. Okay? So draw this out, and then we'll start with, okay, we'll draw a column for A, draw a column for B. So we kind of look, how many variables do we have here? That's 2. We have A and B. 2 to the 2 is 4. So we're going to have 4 rows, A, B. 0, 0, 1, 1, 0, 1, 0, 1. Okay? What do we do here? What I advise, okay, whenever you have a negation in your logic, in your Boolean expression, it's beautiful. It always helps to make it another column. Okay, so how I'll solve this is that I'll have not A as its own separate column, and I'll equally have not B as its own unique column, so that when I'm performing my AND operations, I don't do much work with my head. I can just simply look at it. So how we'll do this? Look at A, not of this A. So now you've got to be careful. You're not handling B. Okay, you're dealing with A and not A and A. So not of A, remember the not operation returns the inverse. Not of A is 1, since this is 0. Not of 0 is 1. Not of 1 is 0. And not of 1 is also 0 in this case. We go head over to not B. Not of B, in this case, not of 0 is 1. Not of 1 is 0. Not of 0 is 1, and not of 1 is 0. Pretty fun stuff. So now we handle, since we've handled A, B, not A and not B, we handle the expressions that are being summed together before we add them finally. Okay? So here, I'll do not AB. Okay, so I sort of shut this out. So give me space. Okay. And here I will have A, not B, to make things easier for myself. So recall the operation here is the AND operation. So now I'm doing not AB, which is not A and B. Recall the AND operation is only high when both inputs are high. So A, not A and B, these are not both high. This is low. So this is going to be a low. These are both high. So this is going to be high. These are both low, low. Only this is high, low. Because it's the AND operation. Doing for A and not B. So these are worlds apart. 0 and not and 1 is 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. Okay, and now the final thing we have to do is the final output. Okay, so you see the reward for our hard work over here. We have not AB and A not B. So now we can add these together with the OR operation. So this is this, and this is this. So we will now treat these columns as if we were adding two normal variables together. ORing, adding, ORing. Okay, they may sometimes call adding OR to OR. OR. Okay. So 0 or 0 is 0. Because the OR operation is only high when both inputs are high. The OR operation is high when any one of the inputs is high. So when I get a 1 on any one of my inputs, my OR, as long as it's the OR operation, okay, comes high. So this is, recall I'm ORing, or I'm ORing these two columns. So 1 and 0, this is high, so this becomes 1. 0 or 1, this is high, so this stays as 1. 0 or 0, 0, since none of these are high. So ta-da, you have your truth table expression for what we have been given. So to draw the combinational logic circuits, I assume we're confident now from what we did in the first question. Okay, we have A over here, and we have B over here. So I think this is going to be a really cool question. A, B. We have to relax over here. Draw the combinational circuit for the following expression. Y is equal to not AB or A not B. So recall we handle each term individually first. So we need to design not AB. So this is not A. So we need to introduce the not gates in our A row. Okay? And output it. So not AB, these are being added together. So we can continue over here. That would work. But you've now got to, okay, we'll continue over here. Join these together. Close enough. Then we can take it close together so that we don't have to draw such a giant AND gate. Okay? So the outputs of this, recall, you have A over here, you have B on this line. This gets negated. This comes not A. This is still B. And you have not A and B entering your AND gate. And so your output becomes not AB. Cute stuff. The second half is A not B. So now we have to design A not B. You've got the A line over here, but we don't have anything to do with B. So what I would do in this situation, okay, is to bring out A. Okay. Draw it out. Bring out B. Draw it out. So that I have space to work properly for my expression. So recall, you have to be very careful now. This is A and this is B. But the term we need to make is A not B. Meaning we need our NOT gate. We need our inverter. Okay? Inverter. We NOT this. It's got to be a cool triangle. Okay. So now what comes here? This is not B. And this stays as A. This stays as A. So now we've got not B and A and two lines beside each other. We can join them together without any qualms in our conscience. Okay? So we can add these, we can and these guys together. Okay? And out will come A, not B. Recall what I said of highlighting the lines these are coming from to indicate your junction. Okay? So now look, you've got not AB and A not B. What's the last thing you have to do? Look at the middle term of this expression. Is the OR gates. So we bring these guys together and we introduce the OR gates to simplify all our hard work. To Paduda. So recall, not AB comes into here, A not B comes into here, and out comes the sum, the OR of these, both of these expressions, okay? Not AB or A not B, which is Y. Ta-da! So this is our combinational logic circuit, and it looks pretty neat from afar. Okay, really fancy stuff. Combination. This is our combinational logic circuit. Okay, so we can see it's not particularly difficult to design. Same thing with logic gates. You just have to be careful when designing your truth tables. If you've got a negation, create a column for your negation. Treat each of the terms individually. Then you've performed the final operation. The same thing goes for here. You have to really be careful as you're designing your logic gates. Remember the difference between and OR gates, how to add them together. All right, so now that we've covered the intro to combinational logic circuits, the next videos will definitely cover more complex, perhaps 3 variable inputs questions, word problems, and how to design that. All right, so I'll see you in the next video.